So we have seen how to find ds with geometrical intuition. That's only possible if the geometry is very simple. We have seen how to look it up on a table, and that's only possible if you are using commonly used surfaces such as a sphere or a cylinder or a cone. And finally, the third, I would say this is the most general method. So if I give you any surface whatsoever, how do you find ds in general? So you follow a mathematical recipe, which I am going to explain now. I made this little figure, which is so small and so simple, but I think it's the best I can do to explain this, okay? So here I'm showing, as usual, a surface defined by two parameters u and v. And here you can see that this curve corresponds to a value u. And now this curve, which is almost parallel to the previous curve, corresponds to a value of u plus du. Okay, so we increased u by a tiny amount du. Okay, so imagine that we are zooming in so much that this surface locally behaves like a plane because we have zoomed in a lot. Okay, this is a really zoomed in version. So we can do the same in v. We can fix a value of v, and then we can increase v by an amount dv, a differential amount. So we move from this line to this line. So then this means that if we fixed u and v, and we increase both u and both v, we end up here. Okay, so this rectangle here will tell us the value of ds. So how can you obtain it mathematically? Well, as I said, if you zoom in close enough, the actual ds, which would be this thing down here, yeah, that is lighter yellow, yeah, this thing here, but up to there, so that would be the curved ds, becomes, in the limit when the du and dv are small enough, becomes identical to this rectangle here formed by these two arrows, the blue and the red arrow. Okay, so that's the advantage of working with differentials, that suddenly we can approximate curves by rectangles. So what is the size of this rectangle? Actually, it's relatively simple. So this red arrow here, which I wrote here as tau v times dv, this is nothing else than the partial derivative of r with respect to v times dv. Remember that the partial derivative of r with respect to v was a vector that is tangent to the lines of constant u. So it's a vector that is in the direction of this red vector, okay? But the length of this vector tells us about the rate of change of the position as we are increasing the variable v. So this means that if we multiply the rate of change times dv, we are obviously going to get how much we move along this direction when we increase v by an amount dv, right? So how much did the position vector move from here to here? Remember that every time we talk about position vectors, we are talking about a vector that points from the origin somewhere to that position. Yeah, so that position vector is changing, and the change in that vector is given by this, which is this red vector here. The change in the position vector when we increase v by an amount dv. By now, this kind of expression, having a derivative times a differential, should be very familiar to you. It's like saying what dr is, yeah? What's the increase in r when we change, when du is 0, but dv is not 0, okay? This is the differential of r. Okay, so this is the vector, the red arrow there. Let me remove this. Good. What about the blue arrow here? So the blue arrow here is going to be very similar. It's just we need to do the differential of r with respect to u times du. Okay, so now this is like the differential of r when dv is 0, but du is not 0. Okay? Maybe I can add that refresher. Do you remember that dr, the differential of a vector, was defined as dr du times du plus dr over dv times dv? You remember this? This was the differential of a vector. So here I'm saying that if we increase only u by an amount du, but we don't increase v by anything, Then we substitute dv equals 0, so this goes out, and we are left with only this, which is this blue arrow. And on the other hand, if we are increasing v by an amount dv, but we are leaving u as a constant, then du is 0, so this goes away, and we are left only with this, which is exactly this arrow here, this red arrow there. Okay, so I hope the definition of these two little arrows makes sense. So now ds is just the area formed by the parallelogram formed by these two arrows. And how do you calculate the area when you have two vectors in 3D space, A and B? They don't even have to be orthogonal, they can be at any angle. What's the area formed by the parallelogram? So that area is the norm of A cross B. You remember that from basic properties of vectors. Therefore, ds is simply the norm of the first vector times the second vector. When I say times, I mean cross product, okay? So we do the cross product between the first vector and the second vector, and we take the norm. Of course, we can now take du and dv outside, because these are just constants, or they are the variables, and we end up with this norm of the cross product of the two tangent vectors. And this should ring a bell, this thing inside of the norm. Remember that this was the definition of the normal vector. You remember the normal vector to a surface, right? So it turns out that the length of this normal vector is giving us the size of ds relative to du and dv. So this length of this normal vector is telling us about the size of these squares when you increase du and dv by a certain amount. Okay? And that's thanks to the fact that the tangent vectors are giving us the rate of change. So they are longer if the parameter is making r move faster, so that the squares become bigger. So there's a lot of visual intuition here. If you feel a bit lost with the visual intuition, my recommendation would be don't worry about it, because the good news is you can just remember this equation, which I conveniently wrote in a golden box, okay? And you know how to calculate this. You know how to calculate the norm of a vector, so you know how to calculate ds. Even if you don't have the intuition for these arguments, hand-waving arguments that I made here, at least you know what the equation is, and you can apply it, okay? Now, before ending the video, if it was for me, I would leave it here. But every time I check books on surface integrals, they actually go ahead and they develop this even further. So they do this. They say, yeah, right, you can write dr du cross dr dv. So dr du is this vector, which is x with respect to u, y with respect to u, and z with respect to u. And then dr, the partial of r with respect to v, is also this vector here, which is the partial of x with respect to v, the partial of y with respect to v, the partial of z with respect to v. So therefore now we do the cross product. So we have to calculate this determinant, and we arrive at this. So this is the equation that most books give for calculating ds. So they say calculate the norm of this thing, this monster. And that's how they do it. So to calculate the norm of this monster, you have to do the squares of each component and then do the square root of that. So it gets even uglier. So eventually they reached here. This is from my notes, okay? So the books eventually give you that this is the equation for a double integral. So no wonder that students that try to read books end up running away from this. This is a horrible thing. Who could ever understand such a thing? In my opinion, I would never remember this thing. Just think about the logic. ds is the norm of the normal vector, and the normal vector is just the cross product of the two partial derivatives, okay? I think it makes much more sense to remember the logic and remember this than having to remember this, okay? So there you have it. That's the general recipe for finding ds for any surface S. So it's this big monster, which has a logic behind it, which is this. So let's do some examples. See you in the examples.